Okay, well, good afternoon. So, thank you very much for inviting me, and thank you, Professor Yao, for the very kind introduction. So, my topic is similar to the previous talk in that it's all based on mathematics, but it's different in that what is studying is not the physical world as the kind of intellectual world. The world of computation in the brain and in living things. And I'll talk mostly about this one recent book I have, but I've worked generally in this area for a while, so I'll mention briefly that two previous books, and writing books is a lot of effort, and there are various reasons why one may want to write books. So the first one was like an academic monograph. I just wanted to write down my thoughts on something which I believed was new, and writing a book gives you quite a bit of latitude in writing what you like. So I enjoyed that. So the second one, called Probably Approximately Correct, is related somewhat to what I'm going to talk about. So that was about machine learning. So this was partly a book to popularize some ideas which had existed in the literature by then, mostly in papers. And so, as I say, it was about machine learning, but just I just have one line from the book. So just to give you some idea of what machine learning is about. So this was published about 10 years ago, before machine learning became so popularized with large language models. And I try to introduce these two words, theory full and theory less. And by theory full, I meant areas like mathematics and physics, where there are some rules, and you can argue, and you can draw conclusions, and there's a theory, and if you put together some facts which you believe are correct, then you get something else which is correct, so there's a theory. And of course, there are other things which have theories which we deal with, like a sport. So a sport has rules, so you can argue about the rules of a sport. And the laws of a country, there are rules, you can argue about laws. So there are these various areas where we're used to logical thinking, like the mathematical sciences. But I was drawn to attention to another area of the theory less, the idea that humans are also capable of doing some things with very high accuracy, even though we don't know exactly what the underlying rules are. So, for example, we are very good at recognizing if someone shows you a picture of an animal, you can recognize whether it's an elephant or not, and we agree to a high degree, so we're very skilled, but we don't know what rules we're applying. So that's the theory less. And maybe the application which we've all seen recently with large language models is being able to compose smooth sentences, say in Chinese or English. So you can write text, very smooth text, flowing text, grammatically valid text, although in fact we don't quite know what the rules are of the game. And these kind of behaviors are all, my hypothesis was that they're all produced by some sort of learning process where you learn by example. And of course, this is exactly what large language models do. They're given lots of sentences from a natural language, and they're trained to predict the next word. Okay. So this kind of learning will be a topic of my next book, which, as advertised, is called The Importance of Being Educable. And I'll try to describe various aspects of what the book tries to do. So one question which I think the book gives an answer to, it wasn't my intent in writing it, was to give a simple view of what current AI is, because the view one gets from the media can be very confusing, and it is confusing. But by looking at the question more generally, one can get a simpler view. But the problem which I'm looking at more directly in this book is what is the cognitive capability there's a word missing there, that humans have that have enabled us to build this civilization that we have built. So what is special about humans which other animals do not have? And this is very similar to the question of what is the potential power of AI, since in AI we essentially ask machines to do things which humans are good at. We always ask computers to do things which we want to do, we wish we could do, very close to human capabilities. Okay, so as I said, so here we're exploring the world of thinking, and the person who first showed that this area could be studied using mathematics was Alan Turing, and he also gave us a license to talk about humans and machines in the same argument. Okay, so he asked, can every task done by humans be done by a machine? So this was a question which everyone asked in his day, and also everyone asks here today. So in a radio broadcast, he famously said that it is customary in a talk or article on the subject to offer a grain of comfort in the form of a statement that some particularly human characteristic could never be imitated by a machine. It might, for instance, be said that no machine could write good English, or that it could not be influenced by sex appeal or smoke a pipe. I cannot offer any such comfort, for I believe that no such bounds can be set. And the interesting thing here is that this wasn't just a philosophical opinion, but this followed from his main science, which came to be known as the Church-Turing thesis, which is that a mathematical model of computation, what became called the Turing machine, is the most powerful kind of mechanism for computing in this universe, including methods of computation by biological, physical, chemical, or whatever mechanisms the world offers. Okay, so this we should take seriously, and I think this we should regard as kind of settled. I should note that there are some philosophical issues which people raise, but these are philosophical. So I think, for example, his reference to smoke a pipe, I think is some kind of philosophical joke, I think, because obviously he did not mean whether you could make a machine which burns tobacco. He presumably meant whether you could make a machine which enjoys smoking a pipe as much as a human does, whatever that is. But these things of perceptions, feelings of computers and humans, these are very hard to discuss with science, and we won't. So we want to discuss behaviors which are externally visible. So, so what I regard as unsettled science, which he didn't settle, so he said machines, humans, the same. But what he didn't say is, well, what are humans and what are machines? What are humans capable of? If we can't say that, then where are we? So how do we characterize what human capabilities are? And we seem to be amazingly bad at this, amazingly. We've studied humans for thousands of years, but we don't have good answers. So, for example, what about human intelligence? I think most people, as a first guess, would say that what's special about humans, what distinguishes us from other animals, is our intelligence. And in fact, we are very obsessed with this. So when we measure our mental abilities, we call the result an intelligence quotient. When we attempt to emulate our mental faculties, we call it artificial intelligence. Some fear that machines more intelligent than humans would be an existential threat. And in searching the cosmos, we are seeking intelligent life. So you would think that we really understand intelligence if we keep talking about it, but we don't. So even the experts don't. Some expert psychologists were asked to define what intelligence is, so we really knew what intelligence tests measure, but they concluded that when 24 prominent theorists were recently asked to define intelligence, they gave 24 somewhat different definitions. So we don't know what intelligence is. And this is consistent with history, that intelligence in the sense of intelligence tests were originally defined not by saying this is how you recognize an intelligent person, but saying that many different tests you do, some people are good at many things, some people are bad at many things, and somehow the correlations between how well you do in many things is your intelligence. But this is a very indirect thing. You would think that we deserve better, that we somehow, if we're judged on whether we're intelligent or not, someone should tell us, what are we supposed to do? So I'm interested in more explicit definitions of our human capabilities. Okay, so this is back to the book. So I'm just summarizing the cover designers. So books have cover designs. And so the question I'm asking is, what is the cognitive capability that enables humans to go from this primitive arrowhead to a computer cursor in a rather short amount of time, a few thousand years, in a period where no one believes that there was significant biological evolution. So it must be that we have some cognitive capability. At the first stage, it just took a long time to kind of come to fruition and create the civilization we have. And the question is, what is this capability? Okay, so I call this civilization enabler, this capability, which enabled us to go from one to the other. And so this isn't a total theory of humans, or even of, okay? So we can leave out many things which we share with other animals, however interesting or complicated they may be. So vision, how we see, how we move, locomotion, our emotions, all these things are very widespread in the animal kingdom, and what's special about us is not any of these. What's special about us is some more higher capability of processing information in complicated ways. And so the methodology, inspired by Turing certainly, is computational. And very briefly what this means is that when I say that we do something, we're capable of something, I want to define it as a function, as an input-output thing. So if you can do something, I want to know what's the result afterwards, which was different from what things were before. So defining what the changes are when you execute your talent. And the second notion is computational feasibility, that if I attribute to you some capability, it shouldn't be some abstract thing which is impossible to do in the universe. It should be something which is realizable in a feasible number of steps. Okay, so this question of what's special about humans has been asked by many academic communities for a long time. Of course, I have a website here where you can look up 617 different topics which academics have studied, in which humans and our closest relatives differ. So which one is the civilization enabler? Again, it's a capability we have which enables us to achieve this civilization we have. So eyebrows are supposed to be unique to humans, but they're not a capability, and there's no theory which says that if you have eyebrows, then you can build a civilization. Similarly, many other things were important in human history, like animal domestication, but again, there's no theory which says that if you can domesticate animals, then you can build computers. So the many other things have been suggested to be special to humans, like collaboration, social learning is learning from each other, intelligence, as I said, not well defined. So symbols and language, so they're getting closer. I'll say more about them in a second. But again, so language isn't a candidate because it's kind of, well, A, it's not really a capability in this sense, but also if you teach an ape language, it doesn't make it want to do advanced things. It doesn't make it make it want to build a rocket to go to the moon. Okay, so it doesn't. This capability isn't enough to make to explain things. So this question of civilization enablers has been asked, especially since the time of Darwin. And so his view was that, among the different candidates, like the ones I enumerated, none of them is a strict explainer of human uniqueness. He thought that in all these dimensions we differ only in degree from other animals. Okay. So what are we doing here today? What does this book do? Well, the main idea is that with these computational notions, I'll define these tasks slightly more precisely using mathematical notation. And because I'll define things more precisely, I can define things slightly more complex. Okay, so if in Darwin's time all you could do is to look at single words in the English dictionary and say which of these is the right civilization enabler, then maybe he was right that none of them was an explanation by itself. But maybe with more precise language we can express some more complicated idea. So maybe we need a more complicated idea than simply a word already available in the language. Okay, so I can briefly tell you what my proposal is. So basically in the book I have a proposal for this capability, and then there's a list of different directions in which one can go if one believes it. Okay, so if one accepts that this is what's special about humans, then there are various consequences. So I'll list those as well, maybe rapidly. So this capability, which I say is unique to humans, I called educability. So it's a definition. It's a compound concept. So as I'll say, it's made up of 3 or 4 different components. So I think that's the complexity it needs to have. So it reminds me of the human capability to be educated, by which I mean something very general, that all the time people look at their cell phones, they read novels, they watch movies, they're all the time trying to take in information. And we can not only take in information, but we can kind of process it, we can associate it with other things we already know, we can use it. So we seem to be hungry for information. And of course formal education forms a big part of human activity. So I'm saying this kind of activity is very fundamental to humans, and I try to spell out what it is in concrete terms. Okay, so I'll give you a quick definition. Then I'll say slightly more precisely what they involve, and then I'll go on to some consequences. So the first capability is what I call acquiring beliefs by generalizing from experience. So by this I mean exactly what one talks about in machine learning as generalizing from many examples. So this is what basically current AI does, and does very successfully. But it's a very specialized thing. It's not everything. It does one thing very well, it's very useful, but it's not everything, and that's why we have to move beyond it. So basically, what I mean by this is what I meant before by how we deal with the theory less, that we see many examples of something, like examples of pictures, and some are of elephants, some are not of elephants. Somehow we can figure out, from this we can learn how to recognize elephants in the future. So the second component of my definition is that once you have learned to learn these beliefs, you've learned to recognize elephants and many other things, then surely it would be a waste if we couldn't combine these beliefs, so chain them together. Okay, so if you're planning what to do, how to get home this evening, then you may make the first step, then the second step, then the third step, and each part of your plan is applying something you've learned, and you're applying it in sequence. Okay, so this is a very natural thing to do. And the third thing is more to do with very traditional education, which is that we can also acquire beliefs by being told the belief explicitly described to us by others. So by belief here, I mean anything like a recipe, a formula for doing something, a prescription, a computer program. So someone explicitly tells us how to do something, and we just execute it. So it's not based on our experience. So this may be a formula you learn in a physics class, which other people have discovered from their experience to explain some physical phenomenon. But you don't have to repeat the experiment. You're just told the formula, and you have all the benefit, which the poor guy who had to do all the experiments acquired at great labor and cost. Okay? So I'll go through these again in a second. So all this has to be in a context which is rich enough. And by rich enough, I mean that all this knowledge can be applied to what I call a multi-object scene analysis, which means that when you look at the world, you don't just look through it through one pixel, which is light or dark, but it's a richer world we see. And you may see in front of you, say, 4 people. You see who's sitting next to whom, and some relationships. So we can examine the world at some detail. And the last aspect is that we also can do symbolic naming. So for individuals, for scientific concepts, we can dream up an arbitrary name for it and then use it to refer to it. I suppose when you call a dog by its name, that's the beginnings of symbolic naming, because you can call your dog anything. Okay, so that's basically the definition. And so educational philosophers talk about many things, but they usually make contact with these things. So certainly number 3 is very traditional education, where you listen in a classroom and someone recites some facts or theories. Number 1 is more hands-on learning, where you do some experiments yourself. And number 2 is that you apply what you've learned to specific situations. So I think most people think that a good educational experience should have some element of all 3. And so these are formalizations of all 3. Now, if you're interested in human evolution, you may want to guess, well, when did humans acquire these capabilities? As I said, it's multiple. And so this is just a guess. I don't need to guess a timeline, but here is one. So certainly, generalizing from experience must be very ancient. So every animal does it. When the most primitive animal in the ocean looks for food, it learns from experience where to find the food. And certainly, if it learns things, it will also combine it. So the aspect which is most recent, the most recent addition, is the last one, that we can follow instructions given to us by others. Of course, for humans, this is done mostly through language. So in fact, most of the things we do, knowledge we transfer to each other, would be hard to imagine without language. But in principle, animals can also be taught complicated things by demonstrating physical things. So it's believed that our species is about 300,000 years old, and so a reasonable guess is that our basic capability came together before our species emerged, merely because people have searched for biological changes in humans in the last 300,000 years, and nothing amazing has been found. So it's not conclusive, but it's quite possible that we started with this capability, and it just took a very long time for this capability to become so useful. It's like a snowball rolling slowly and becoming bigger. As our knowledge increased, it became more and more useful to gain more knowledge. Okay, so so very quickly I'll go back to through the three components. So generalizing from experience is I identify with the classical picture of machine learning by example, which is that you have some learning algorithm, and it takes examples with their labels, so maybe pictures labeled according to the species according to what the picture shows. And then this learning algorithm generates a classifier, which is another algorithm, and the other algorithm will then classify new examples according to the label. Okay, so this is classical machine learning. And as we know, if you do machine learning, is that it's important that where you learn from, the world in which you take the examples should be the same in which you test your classifier. That if you learn but the world changes too much, then what you've learned isn't useful. So to make this model more concrete, so this is probably approximately correct model of learning, whose main feature is to give a quantitative constraint on what you need to realize before you declare your machine to be really learning. And the constraint is that the accuracy of predicting new examples should increase, so the error should go down as you've put more and more effort into the learning. Okay, so maybe you learn from 1,000 examples, 1,000,000 examples, 1,000,000,000 examples. As you learn from more examples, you have to do more computational steps. As you put in more effort, you should be rewarded by being able to classify in the future more accurately. And in particular, this requires that the reward, that it goes down fast enough, error decrease fast as some sort of algebraic law, which in more concrete terms means that if you increase your effort 10 times and you halve the error, then when you increase the error another 10 times, you should halve the error again. So this is like an adequate reward for spending more and more money on training these nets. Okay, so this is learning from example, and this is, as we know from experience, this is a powerful way of doing this. So second part was training beliefs, and here the phenomenon is that what we're training are these classifiers which we've learned, and these classifiers will make errors. Okay, so when we chain together things which make errors, we have to be careful that the conclusions we draw are not nonsense. Okay. Now, this idea of combining uncertain things has been discussed, but not that much. So just to give a quotation from the world of politics, actually Winston Churchill may or may not have said this, I'm not sure whether he did, but he said, true genius resides in the capacity for evaluation of uncertain, hazardous, and conflicting information. But I mean, what I want to emphasize here is that I mean this almost ironically, in that dealing with hazardous and conflicting information is what every little animal has to do from the start. So life is full of dealing with avoiding predators, etc., etc. So having a principled approach to combining uncertain information is something which is kind of a very essential part of life, and in the system one gives it a first-class status. And so I've got a system called robust logic which does this. It's not like standard logic, it deals with facts which are uncertain, but it's got an analog of soundness. So soundness in logic means that if you combine two things you're sure of, the conclusion should be sure, as long as the method of combination is in your rule book. And again, it should be computationally feasible. And very roughly what this corresponds to is that in in the standard learning scenario, we've got one big box. This is a supervised learning box, as in what I started with. And in this robust logic, what we'll do is we'll learn many boxes. We're still going to learn many things. Maybe you have a separate box for each word in the Chinese language. And then when you look at something, some of these boxes will say, yes, these words are recognized. And then you can chain together conclusions through these different boxes to reason, to reach some complex argument. Okay. So the standard back learning gives you guarantees for generalization, and with this you also get guarantees when you chain together different things you've learned. And very basically, for example, if you got two rules which you believe to 99% confidence because they're really supported by the data you've seen, then when you chain them together, it may be reasonable to expect 98% accuracy in the prediction. So you want some lower bound on how reasonable it is to combine information. Okay, so as far as what complexity the world has to be described with, so this is some crow, a clever bird, which is given some experiment to do. They're very good at figuring out solutions to hard puzzles. So here it's something like you've got a glass with some water in it, and there's a seed floating on it, and the bird figures out that if you put stones into liquid, then the water level will rise, and it'll be able to eat the seed. But the point is that this scene has to be understood by the crow to some detail. And so, for example, the fact that there's a glass is one object, the water in it is something else, there's a seed, there's a water level, the water is in the glass. So all these basic relationships somehow has to be in the information which this bird has. So there has to be some richness of description of the world for any of this to make sense. And okay, so this is just an illustration, a different illustration. So how this works is that, so maybe the system, okay, so these dark circles are called tokens here. So when you wake up in the morning, you may think of your dog, and you may also think of the relationship that your dog likes something, and you may wonder what your dog likes. And how you'll solve this problem is that you bring up from your mind you conclude it's a bone, but how you'll do this is that you will bring up in your mind a classifier which predicts what that object is. So a classifier which predicts bones or not bones will be the one which tells you that this missing object is in fact a bone. So how these things work is that using machine learning, you're going to learn maybe a rule which predicts bone, and the rule will in fact be a classifier. So if you like deep networks, this will be a deep network. If you like some other representation like decision trees, this will be a decision tree. Okay. But the idea is that in your mind's eye, you have this picture, your dog likes a bone, and then maybe you predict the next thing by using another rule. So this is how in our imaginations we can make plans and we can make deductions by giving partial information and applying what we've learned in sequence in a chain. Okay, so for a situation in mind's eye, you chain the applicable learned rules. Okay, so just one example, especially for people who like machine learning. So if you ask a human the question, did Aristotle own a cell phone? Most humans can answer this correctly in a fraction of a second. But this question doesn't look like a good question for a pure machine learning system, say based on information on the internet, because there isn't very much information about Greek philosophers and their personal possessions. Okay, it's not what's listed on the internet. Okay, so obviously we solve this by doing some sort of chaining. We have some information about when Aristotle lived, when cell phones were invented. We chain things. So the theory is that we solve this by doing some sort of chaining and reasoning, and we can put this on a theoretically well-founded basis, but this is beyond the simple machine learning paradigm. Okay, so let's go on to the next thing. So the last component of this educability was taking instruction from others. So what this amounts to is that given everything I've described, if someone else has a belief in their heads, they can just tell you the belief and you'll know it, you'll be able to execute it. So you can receive explicit beliefs from others, and mathematically this is just like a universal Turing machine. Okay, so educability is the realization and integration of the capabilities I've described so far. And just to summarize the benefits of this last thing, which are kind of the obvious, that if you can tell people your discoveries, then they don't have to go through the painful process of doing them. And in fact, one person can tell 1,000 people their discovery, saves 1,000 people from discovering themselves. Also, some of the discoveries people make are very powerful discoveries, which are methods of reasoning. They're not just arbitrary facts. So, for example, arithmetic, someone must have discovered, and without arithmetic, we couldn't do very much science. And this is, again, arithmetic is something which we teach each other. So the accumulation of science with contributions from thousands of individuals, that all needs this part 3 of what I'm saying. And this has enabled technology to become so broad, go to the moon, build computers, cure disease. And also, we have complex human cultures. So as a diagram, the idea is that we live in a complex environment, and basic machine learning, back learning, and reverse logic are all about adapting to this complex environment. And in some sense, if your environment is stable and you've learned where to find food, then you're safe to go and find food the same place tomorrow because the environment is stable. But when you go on to acquiring programs by instruction, so if someone tells you something in a lecture room, is that safe? I mean, how do you know it's useful? How do you know it's true? Of course, all this is in an education system. This is all based on trust, which is necessary. But once you acquire beliefs from others without having seen the evidence for it, so in the first two things you see the evidence, and for the last thing you don't see any evidence. You just have to take someone else's word for it. So okay, so I'll just now quickly describe 6 differences, which, if you take this theory seriously, this may make. And the first one follows what I've just described, that the fact that we're so educable, we can pick up information so fast in the ways I've described, is very good. But the third aspect is dangerous in that we can pick up recipes, formulae from others, facts or pseudo-facts, without being able to verify whether they're true or not. Okay, so then we're easy victims of arbitrary belief systems, ideologies, conspiracy theories, misinformation. So the idea is that I've described lots of ways in which we can process information and acquire it, but I haven't described any way in which we can verify whether what we've learned is true in the world we live in. So I think it's a fundamental problem that there probably is no way in which we can verify the truth of something, but we're told what the result of an experiment is, we're told what happens on the other side of the world, we're in no position to verify it all. We have to take it on trust. But in some sense, we have to recognize that this is a basic weakness we have, and we may benefit from recognizing it. Okay, so a different direction. It would be great if we could improve our educability. What if we could learn faster, etc. So how do I improve my educability? Well, this question only makes sense if we can measure educability. So a sub-question is, what would the test for educability look like? And in some sense, the answer to this is the simplest thing I'll say today, because a test for educability wouldn't test for your previous knowledge, it wouldn't test for your previous traits, it would only test how well you use knowledge which you've gained during the test. So the test starts now, you will be given some information, and then you will test it on how well you've acquired the information, how well you can generalize from it, how well you can reason from it, whatever. But this wouldn't be a test for any skill you already had or any knowledge you already had. The only skill would be a test of educability. So in some sense, this is an extremely simple idea, and it may be hard to realize in a pure sense, but it's a very simple ambition. And for example, typical IQ tests like if apple is to seed then, this doesn't test educability because I haven't told you anything new. I'm testing you for your previous understanding of some relations. Okay, so this is not what we want. Okay, so next I want to emphasize that educability has many parameters. So mathematically, there's a downside. We like mathematical models which are very clean, but here it's the opposite. And so, for example, if I have a standalone system, which is educable, intelligent, machine learning, whatever, then one fundamental question is what is its belief choice policy? So does it believe everything is told? Does every labeled picture, does it believe every theory is told, even if it's contradictory? So we know that humans have quite sophisticated ways of deciding whom to believe. So children believe their parents first, later on maybe they believe other people, we believe people in authority. But so this is a parameter of any machine which is in any sense educable, and in this sense already there isn't a unique best way of doing anything in this area. You've got choices of what belief choice policy you have and of many other parameters, and this is a feature of I think it's so having many parameters is not a bug of this concept. I think it's a feature of cognition that we're all different, we're good at different things, we have different knowledge in our heads, we're very incomparable, and I think cognitive systems will be incomparable in a similar way. Okay, so singularity. Some people worry that ultra-intelligent machines will seize control of the world and treat us like dogs. So I don't worry about this so much. In fact, not at all, because these arguments are usually based on some mystical notion of intelligence, which is not defined. But if we define capabilities in this very prosaic, understandable components, so what I've described, you learn from examples, you chain things together, you do some universal Turing machine stuff. It's all very prosaic, so why be afraid of that, even if machines can do it faster and on a bigger scale than us? So, for example, it's possible that all there is are the capabilities I've described. Maybe there are more, but supposing there are only these, with all the parameters that machines will do these very basic kind of tasks with many choices. They'll make many choices in their design, and they'll all be different, incomparable. They'll do everything faster than we can, but we shouldn't. It doesn't seem to be such an existential threat anymore if you spell out what these capabilities are. Okay, so fifth, studying human behavior. Social science theories are different from, say, physics in that there are usually many different approaches. Also, sometimes social scientists are believed to have gone badly wrong. So 100 years ago, the eugenicists thought that nature, thought that nature was much more influential than nurture, and they gave the emphasis they gave to nature over nurture was much bigger than we would now. And generally in social sciences, the difficulty is to draw conclusions about human behavior that are transferable in time and space. So generally so I'm supplying here a word educability, and basically what educability does is to give a word and some mechanism for nurture. Okay, so when we say that human nurture is so important, well, what is nurture? So exactly in what way are we influenced by our environment? And so educability is an attempt to spell out some ways in which our environment influences us, like we believe what we're told. The examples we see, we generalize from. Lastly, education. Well, clearly there are links with education. Would be nice to have a more scientific basis for education than we have. So education, I think, is mostly based on best practices, endeavors around the world. So, of course, some people do study systematically, like what's the best way of teaching reading by doing surveys and trying different methods. But one would think that if we studied the basic processes by which we acquire information, then maybe we could say more about education. Okay, so thank you. I'll stop there.
Thank you, Professor Valiant, for this fascinating talk. Questions now from the audience? Yes?
Hello, Professor. I want to know what preparations should middle school students make to embrace the upcoming era of comprehensive artificial intelligence?
What's the word you used before artificial intelligence?
Comprehensive.
Comprehensive. Well, I think a big question is what is comprehensive artificial intelligence? So in some sense, this educability framework, I think, is one suggestion for what artificial intelligence can be, which is realizing these capabilities. So I think I find it very hard to answer your question because artificial intelligence, machines being able to do these things very efficiently, will cover all aspects of our lives. It'll cover everything. So whatever you do, you probably have to anticipate that machines may be there to help you or hurt you. So I think you need, so I don't think there's a general answer. So I think in whatever particular area of activity you're interested in, you'll have to, you can't ignore AI. That's what I would say.
Hey, other questions? There. So, who wants to ask? Yeah. Maybe we'll let
Hello, Professor. I've noticed that in machine learning, the computer usually takes in like a large set of data, but conversely, as for humans, we can make generalizations or we can extract theories from a rather small set of data. So how is that? So in your point of view, is it possible that through some type of like mimicry for the human brain structure, or through other type of more efficient algorithm, that one day the machine can take in a set of data that as small as necessary for humans and still make valid generalizations and inferences? Thank you.
Yeah, so that's a great question. I think the situation now is that standard machine learning is very successful, but people make the mistake of equating that to AI. People take it too seriously. Okay, so what I'm suggesting here is that we're capable of we have a series of capabilities, one of which is generalization, and if we exercise these capabilities together, then we can do these many things we do. So, for example, there are also capabilities I haven't described because I think other animals can do it as well, like recognizing an individual. Okay, so the fact that I can recognize an individual is different from generalizing from many examples, and I can do it on one case, but other animals can do it too. So saying that we recognize individuals by doing generalization, that would be a mistake. But I think the one example I'd draw attention to is my example about Aristotle and his cell phone. So this was a case which I suppose you couldn't learn at all from examples with standard data sets, but you can do with reasoning. So I think many of the phenomena which I think you allude to that we can do with few examples, we do by having previous knowledge and using reasoning. Okay, so I think you have to use these different capabilities together to get the phenomena we find in human performance. And it's a big mistake to think of just vanilla machine learning as being everything. It's not. It's very, very powerful, but thinking of that as being AI is wrong.
Right. So deductive reasoning plays a huge part in like intelligence as well as
Exactly, yes.
Thank you, Professor.
Okay, does this answer your questions as well? Okay, maybe you let you ask also.
Hello, Professor. I want to ask that if we can enable AI to have the same mechanism as we think. In another word, can AI think like humans? It could be AI could have a larger know more about it, know about everything. So can AI think like human and help our science development? That's all.
Yeah. So could someone summarize the question in one sentence?
It's about that can AI think like humans and help our science development?
Can AI think like humans and help?
Help the scientific development.
Help the science. Well, I think I think AI and humans, I believe, have fairly more similar thought processes. AI can have similar thought processes to humans, and I think they can help. Will be able to help scientists. So at the moment, they're helping scientists just in the way of standard machine learning because that's what's being implemented. But if kind of reasoning is added to these learning systems, then I think the machines will be more useful in helping humans in the sciences. But they already are very useful because powerful application of just generalization, like in protein folding, is very powerful.
Okay. Other questions?
Good afternoon. I have a question. However, with the rapid development of technology in the context of the continuous progress of artificial intelligence. It is possible for humans to overlay on missions and external information, thereby gradually weakening this unique ability of this urn.
So can you summarize the question?
Yeah, right. That's what I want to do, yeah. So basically you emphasize the importance of abilities such as generalizing from experience, training beliefs, and accepting instructions from others. However, with the rapid development of technology, especially in the context of the continuous progress of artificial intelligence, is it possible for humans to overly rely on machines and external information, thereby gradually weakening these originally unique abilities of their own?
Oh, I see. Okay. So, yeah. So, do we become stupid if we rely too much on machines? Yeah. Well, who knows? Obviously, if we push things to extremes and we don't use our brains at all, then all kinds of things can happen. But personally, I'm not afraid of that. I think we'll always use machines to simplify some things which were previously complicated, and I think we usually move on to then do other things with our brains. So I think what you're suggesting could happen. I can't prove to you it won't happen, but personally I'm not so worried about that. Okay.
Yes?
Hi, Professor. I'm a student from high school affiliated Renmin University of China, and I'd like to ask a question. For future, AI might be able to help scientists to do experiments and explore physics, but sometimes for the equations, as the previous professor has said, equations are not very precise, and also the data is not precise. So might there have a very big mistake and error for the model to build, and thus cause mistakes for the results that AI have produced for scientists to discover the future?
In your question, so what is the source of error? Is the AI the source of error, or experiments?
The AI, would AI cause big mistakes due to error for scientists to produce and explore physics in the future?
Yeah. So you're worried about the AI systems making errors?
Yeah, she was also referring to the previous talk where basically you can have a phenomenon which apparently, given a few data sets, seems to be following a certain law, but it's actually not, and the AI might extrapolate from that and do some huge errors. Yeah, is that correct?
Yeah, but I mean, the AI would, I'd guess, would make similar mistakes to humans. So from the information I have, it's not obvious that the AI would make more mistakes or less mistakes than humans. Okay, so I mean, the main thing for AI to do, I think, the main program for AI scientists is to make AI more trustworthy. So if the AI isn't trustworthy, if it's unreliable, then that's terrible, and you shouldn't trust it. Okay, but so I think that's what I think is important. That with AI, the trustworthiness of the system is critical, and the users will know. I think if you use a system well, you'll know how trustworthy it is. But
so it's important for AI to help scientists produce the theory and use scientists to do the experiments to prove the theory that they are reliable and correct?
Well, I think the AI should be used in wherever it's useful. But I'm saying that if you've got special concerns that the AI is unreliable, if that's your main concern, then I mean you're correct in having that main concern. Everyone should have the same concern, but the result will be that AI systems will be developed which are more reliable and more trustworthy. And people who use it will know exactly how much to trust it.
Okay, thank you very much.
Okay, so I guess we just have time for one more quick question. So,
hi, sir. I have a question about human and AI are quite similar, and so if like human can learn with acting and living, and while AI is like first we need to train it, and we can predict that, and it's a separate two thing. But in human, it's only like mixed together. Yeah. So is there any possibilities for AI to train like humans? Like we can learn by experience, and also we can adjust the parameters to make the AI model predict better, and during the development and in actual exercises.
So can you summarize the question?
Yeah, so you basically say whether the AI can learn more like a human by also doing, by developing in a similar way in an environment. And not just data, but then also undergoing some development, some other situations. Is that correct?
Yes, so I don't see any reason against it. So you'd, like we are, it would have to be a standalone system which just stands there, and it'll have to have these parameters which tell it how to update itself, where to find new information, and the kind of things which humans do. So in principle, I don't think there's a fundamental limit to that.
Okay. Thank you very much.
Okay, so let's end the question and answer session at this point and have a short break. And let's thank again Professor Valiant for the wonderful talk.